I'm Tim Ventura, and we're joined today by Dr. Ron Evans, the former head of Project Greenglow, an ambitious attempt to develop breakthrough propulsion technology undertaken at BAE Systems in the United Kingdom. Ron is a mathematician who joined British Aerospace in 1978 as an expert in fluid mechanics. He launched the BAE Gravity study in the hopes of developing disruptive aerospace technology. The study became Project Greenglow and is generally recognized as the most rigorous pursuit of gravity modification and advanced propulsion research performed in the UK. In this presentation, Dr. Evans will discuss gravity and gravitomagnetism, inertia, freefall, the effective mass of a photon, Einstein's gravitational redshift, and offer speculation about electromagnetic and gravitational coupling.
So the first slide is the cover of my latest book, the drawing, which is very wishful thinking, flying saucer on the moon propelled by gravity. And the drawings are all done for me by somebody called Dave Windett. I used to work with his dad when I worked for BAE Systems. So the book is in three parts. The first part talks about the theory of gravity from Newton up to Einstein. The second part of the book deals with the importance of analogues. And I'm a mathematician, and analogues are so important to me. The third part of the book deals with Faraday's gravity experiments and also extending the gravitational theory by using an electromagnetic analog of gravity. The last couple of slides, we may find that after I've shown them to you, that they become secret. I don't know. I'm getting very frustrated. I don't know whether to tell people what I'm doing or say nothing and it all dies with me. So it's a risk. Next slide, please. So this is the analogues. This is somebody called Francis Bacon. He was a politician and he blotted his copybook. He did something he shouldn't have done, and so he got booted out, and he spent his time talking about science. He did a good job. He wrote his book, which is called, if I can find it somewhere, down there, Novum Organum Scientiarum. Anybody speak Latin? I'm afraid I don't. But the book was very influential, but only after Bacon had died. 30 years after his death, there was a group of people who had what was called an invisible college. In the United Kingdom at that time, the Civil War had been going on and you kept your head down. You didn't make a lot of noise. And so they had an invisible college. And at the end of the Civil War, when Charles II became king again, they made something called the Royal Society of London, which is now world famous, of course. And the idea is that if you have some sort of mathematical model of something, and you then strip all the outside of it off, so you're just left with lots of numbers and equations, and then you look at something else, you find, hang on a minute, it's the same model. I've just changed one thing. One thing might be mass, another thing might be charge, and something else might be heat, and so on. You suddenly find the mathematician has suddenly got an insight into things he never realized were there before. Next slide, please. So these are two analogues. The one on the left, electromagnetism, was done by James Clerk Maxwell during the 1860s. He got his ideas from Faraday. Faraday, I think, also worked from analogues, but they were in his mind. He could look at something and think, oh, that's just like this, so I'll try an experiment. So there we are. The dot, if for those mathematicians amongst you, deep was called a divergence for things that spread out, and the curl at the bottom was something that Maxwell introduced. It's if you grab hold of the H as a line and you give it a twist, that's the curl. Maxwell said to himself, all right, I like analogues. I'll have a go at doing it. So he wrote out the equations that he thought might extend Newton's theory. The first one comes straight from the inverse square law, so that's true. The second one, it's true anyway, but we don't know what H is. It's a field, but what is it? No idea. Second one, is true, especially if the G is the gravity. If gravity is not changing, then we get a static case, and we'll look at that in a moment. And the last one is very important, but we've never really realized it in operation. Next slide, please. This is a guy called Oliver Heavyside. He taught himself mathematics. He was absolutely brilliant at it. Now, in this slide, that column at the top in grey is moving with velocity v. It's a steady velocity. And around it, according to the analog, there is a field. It's in green. Outside the body itself, it's so weak, no one has ever seen it. Inside the body, some people think it's quite large, but we don't know because we can't see inside the body. So Oliver Heavyside said to himself, the same as Maxwell and the same as others, if I look at the analog, what is it telling me? I'll compare it with magnetism. If I've got moving charge, I get a magnetic field outside. And I'm guessing if I have a moving body with mass, I will get a gravitomagnetic field outside. Next slide, please, Tim. Now, this is the important one for me. I'll read it to you at the top. It says, the curl of gravitation. Don't forget, if I've got a gravitational line and I grab hold of it and twist it, I get a curl. So there we are. At the bottom, you can see the G at the back there. If I twist around it with the black circle, you can see I'm getting the curl of G. And it says it's equal to the change in gravitomagnetic field. So when the body moves and the velocity changes, we get acceleration. And it says that when you get acceleration, there is a change in gravitomagnetic field, which causes a curl of the gravitational field. Now, mass, that mass there, that grey cylinder of mass, only responds to gravity. So if you think about it, if you sat in the car and you accelerate forwards, you get forced backwards. Have you ever asked yourself, why am I forced backwards when my mass of my body only responds to gravity? Although you haven't realized it, there's a gravitational force pushing you back. It's an induced gravitational force, and it comes from the changing gravitomagnetic field. But we can't see the gravitomagnetic field, but we can feel its effect. Next slide, please. This is a strange one, because if you now drop your mass, I've just told you that it's going to cause a gravitational field. So if the body is dropped in a gravitational field, it will accelerate. And we know that from, my brain's gone. Who's the Italian who first did this? Anyway, if you drop a body, it accelerates with the acceleration due to Earth's gravity field. And from the previous slide, we know that there's an induced gravity field in the opposite direction. So we've now got two gravity fields operating on that body, and one cancels out with the other. So when you drop in a gravity field, you haven't got any inertia because it's been cancelled. So if you've got a spring balance and you try and weigh something while you're falling, you won't see anything. So it won't weigh anything. And this apparently was one of Einstein's happiest thoughts, which led him on to general relativity. You'll find that in my book. It's a long story. Next slide, please. Right, we're going quite fast, Tim. I hope it's okay. We might finish early. So what did Bob Lazar see? In 1998, I'll just look at my notes. I watched a film on the UK TV, and it was called Aliens Among Us. And it was produced by Timothy Good. Tim, good. I taped it, so I've still got it, and it fascinates me. I look at it from time to time. I think, oh, amazing. I think the fascinating thing about it was Bob Lazar said that the technology he was working on came from aliens. Now, I used to know someone who worked at Area 51. He was actually British, or perhaps he was an American. I don't know, naturalized American, I don't know. But he said they did have a place where they tested alien technology, but it wasn't extraterrestrial. It was aircraft from foreign countries. So whether Bob Lazar got mixed up there, I don't know. According to this 1998 video that I watched, there was somebody on it called Stanton Friedman. Some of you may have seen the program or seen the American version of it. And Stanton Friedman said, look, this Bob Lazar is pretty smart. He's a clever guy, but he's got no professional qualifications. So you've got to take with a pinch of salt, as we say in the UK. If he tells you that something he saw works like this, it may do or it may not do. But what did he actually see? That's the question we don't really know at the moment. The next book, that was Timothy Good's book, which I've got here. And then there's the other one by, this one I quite like, it's got a bit more information, by Paul Violette, I think his name is. And in Paul's book, he gives you a little bit more information. It's all very limited. So for a long time, I've been looking, what actually did he see? You couldn't talk to academics about it because they would say, have you been taken in? It's all a lot of rubbish. It's nuts. So I didn't talk to anybody about it. I talked to some of my colleagues, but nobody else. And over the years, I sort of thought about it. Did he see it? And when these books came out, I bought them and had a look. But there's nothing there that I could really say, well, I understand it. He talks about an antimatter reactor. Well, I mean, I've looked on the web and I'll try to understand antimatter reactors. It's not a technology that's going to come very soon as far as I can see. When I looked a bit closer, both of them mentioned the idea that gravity could be channeled in a waveguide. And as Paul said, that's rubbish. If you've got gravity, it just goes through all mass. You can't stop it. So it can't be an ordinary gravitational wave if that's what he saw. Well, that bit stayed with me. It cannot be exclusively gravitational. And I've been thinking about it off and on. When I did my latest book, again, I concentrated on the second third, on trying to expand the analogues. And one of the analogues I looked at, of course, was thermodynamics. I did ideal thermodynamics mostly because I didn't want to bring friction in. I have mentioned friction, but without friction, it's a very nice analog. And I was looking at the analogues, and that led me on to something else, which I'm going to mention in a minute. Next slide, please. Yes, so it's frequency, it's got a wavelength, it's got an energy. This is Einstein's E equals mc squared, of course. And from Planck, we got E equals hf. H is Planck's constant. It's tiny, but he didn't know what H was. He didn't believe it to begin with. We now know that H is a fundamental thing in physics, but he didn't know. It's interesting to me that H is an angular momentum, and it relates to the gravitomagnetic field. Now go back one, please, Tim. And so the photon will have an effective mass. If you tell academics a photon's got mass, they'll tell you you're balmy. So I'm having to call it effective mass. So there it is. It equals hf over c squared. If it's got effective mass, you can guess that light or photons, if they go near a very massive body with a big gravitational field, they'll get attracted So that's on the right, that picture there. A photon from a star will get attracted towards the sun. This was something Einstein first suggested. And another bit that I put on is that a photon has an effective temperature too. Again, from Planck's work on doing black body radiation, you can look at all the curves that they came up with, and there's what I've called Wien's forgotten the name of his Wien's equation. He shows that for the maximum energy of a photon, the wavelength for the maximum energy times the temperature is equal to a constant. So we've got temperature and wavelength. So temperature, wavelength are going to be related. Next slide now, please, Tim. So this is something called Einstein's gravitational redshift. He was a clever man, came up with it back in 1905, I think. It was tested by Pound and Rebka back in 1960. They used gamma rays. Unfortunately, by then Einstein had died 5 years earlier. They used something called a Maxwell effect. It was I described it in my earlier book, which some of you may have seen, which is that one. So I've described how the Pound and Rebka did the experiment. So they showed it works, but it's for gamma rays. No one's ever seen it for light rays, as far as I know, although with satellites, they are trying to do it, or I think they may have done it with microwaves. The only thing about satellites is it's not a straightforward gravitational redshift because the satellite's moving, so you've got Doppler effect coming into it as well. Anyway, just by assuming the photon has an effective mass, and we're all familiar with the idea of a gravitational field, and you can move things up and you can drop them. And if you lift something up in the gravitational field, it gets more energy, so that when you let go, it drops down again and loses energy and turns into kinetic energy and so on. Just by using the fact that photon has mass, we can work out as it moves up, it changes energy. But we've already seen that the photon has energy HF. So if you move the photon up in the gravitational field, it changes energy, but its energy is HF. So if it's changed energy, can't change H. That's a fundamental physical constant. It means that the frequency's changed. And Einstein came up with this formula, which you can do yourself. It's fairly easy to do. No one ever tells you what's actually going on. If you just extend it a bit more and do the rate of change of frequency, you can work out the force on the photon is the change of momentum. And it turns out that what's happening is that the total change of momentum is zero. So there's no force on the photon. What the photon has done in changing frequency is created a gravitational field, just like I showed you for inertia. It's created a gravitational field which cancels with the Earth's field. So that photon beam going up doesn't experience the gravitational field at all, just carries on moving at the speed of light, c. Now, that's okay. If we look at it with the gravitomagnetic view, you can actually see it. There's our photon at the bottom. It's moving up in the gravitational field. Because it's moving up, it's changing its gravitomagnetic field. Outside, you might just be able to see it. It's so weak, you can't see it. But inside the photon, we're assuming it's large, and it's changing because it's changing frequency, it's changing effective mass. As it changes, if you go back to my curl G equation at the beginning, you see it creates a gravitational field. That's the one that cancels with the Earth's field. So that photon there is moving up with no force on it. Next slide, please. I put this in because before I talk about the next step, This is something that somebody, when I worked, sent me this book and said, you know, you're interested in UFOs, read this. And the one page that I really like is page 110, if you've got it. I've got it somewhere. Whoops, up here. I quite like it. You may have seen it. What I want to bring out from it is the fact that the three main things that are associated with a UFO coming into land, the third kind or second kind rather. So you're not actually, I think it's extraterrestrials is the third kind. So this is the second kind. UFO very near. People say there's an electrical interference effects, car radios sometimes play up. Some people say there's a feeling of heat. And there's also a gravitational effect. I feel lighter. In fact, I think somebody claimed that their car tried to lift up slightly. So those are the three effects. If it actually lands, then there's more. It causes damage to things. Next slide, please. So this is my analog now. These are my last two slides. As I said, once I've shown them to you, you might find that people say, no, we can't tell other people about this. Right, so we start off when we do the analog. Let's assume on my left-hand side now, we've got a waveguide, which is filled with something that allows photons to move through it. So it could be a dielectric if I've got a photon source, which is beaming in microwaves or millimeter waves. What I do with the insert, whatever's in that waveguide, the dielectric, is I create a temperature gradient across it. Don't ask me what temperature gradient. This is a suck it and see experiment. We'll have to look at it again in a moment. But now, right, what I should have said was, can we go back 2 slides, Tim, just for a moment? That one, yes. What I didn't mention was it cancelled out the gravity field, but you've now, those photons going up there are changing frequency. Each photon and its frequency is associated with a temperature. So what we've got going up there is a change of temperature as well. That's not cancelled out. You've got a cold shift. So back to the slide we were on, please. So now when we're going up, we're going to come up with a very similar formula to Einstein, only now we're assuming that the photon, as well as having an effective mass, is also an effective heat source, which changes as it goes up the temperature gradient. So when we change, as it changes there, creates a change of gravitational, a change of frequency. So what it does, as in the previous case, the analog says, oh, as that photon moves up the temperature gradient, it creates a change and in frequency and gravitomagnetic field. And in doing so, it cancels out the thermal field T. So it just carries on moving at the speed of light. Speed of light in that material, of course, not the same as the speed of light in air or in space. But just a minute, we've said it cancels out the thermal field, but in it's exactly the same way, this time it's created a gravitational field as well. This time the gravitational field hasn't been cancelled. So in doing this one, we've created a gravitational field in a waveguide. So this made me think, hang on a minute, Paul Laviolette was saying, what Bob Lazar saw was an was a gravitational effect, which he said could be put in a waveguide. But Paul Laviolette said, no, it couldn't, because you couldn't control a gravitational field inside a waveguide. But in this way, you can, because you are creating it within the photons. So the photon density is going to be important. So where you channel the photons is where the gravitational field goes and where the electromagnetic wave goes. So It may be very weak, it might not be, I don't know. We would like to know how to amplify the field. Now, just as an aside, on the right-hand side, I put a picture of Roger Shaw's electromagnetic drive. There's a few people's guesses at how it works. A lot of people don't agree with Roger's quantum theory view. There are other ideas. So I'll put this in as well. What happens, I mean, I used to work on stealth, of course, and one of the things about stealth is the intakes. They show up quite a lot. And one of the ways of stopping them showing up is to make them smaller so the waves can't get in and get reflected back out like cat's eyes on the road. So what happens here as that wave goes up towards the red end, the waves are getting, well, they can't, you've got to have a complete wavelength as it moves up. If you can't have a wavelength, then the wave doesn't exist. If the wave doesn't exist, the energy's there, it's got to go somewhere. So the energy goes to the cavity. So by having that conical cavity and shining the microwaves in it, you're going to find that you get a temperature gradient. Now, if the model I've suggested from my analog on the left-hand side is right, this might say, well, in that case, what we are doing is getting exactly the same effect, and we're going to get a thrust on that cavity. So maybe this is another way of having a look at Roger Shaw's drive. Maybe we should try putting a heating collar around one end, see whether changing the temperature gradient makes any difference. Right, on to the last slide. This is a very suck it and see slide. So there you are, that's my drawing. I'm very frustrated. I'm not an experimentalist. I've looked around to people and said, you know, who can do this for me? So any of the people in the audience that think they can do it, I'd be delighted. I can't work with microwaves, but I can work with light. So what I thought was, well, I'll start off with, I'll have a go at doing it myself. I'll get a piece of glass tubing, which I got, and I've got a laser pointer, and I thought, well, I'll point the laser in the glass tubing and try to get it to go down there. By the way, the first person to do something like this was Faraday back in the 40s. He was the one that really started shining light down things like this. And this is where the Faraday effect came from, because with his analog in his mind, he came up with what was called the Faraday effect and the magnetic field around things like that. Anyway, getting back to this experiment, I've shone the laser along the glass tube. Wow, what it was rubbish. I just couldn't get the laser to go in. It just reflected off the front face of the glass tube. If you're a fiber optic experiment, if there are any of you fiber optic experimentalists in the audience, you will say to me, what you need to know is this. You do something and then the light will shine in the tube. I mean, we know it works because all our telephone systems use fiber optics now. It's all based on light shining through them. So it must work. Maybe we need a bigger laser. I don't know how to do it. So I'm looking to you experimentalists to tell me. So we can start off. I want to create a temperature gradient across it. So you can see the shading that's supposed to be lagging, keeping it so it doesn't emit heat radially. So I can create a temperature gradient. So I'll start off, let's supposing I could make it work for the moment. And I measure the weight, and I then suspend it from a string horizontally. So I have to check everything out, make sure it's balanced. Then I have to shine the laser in. And what I don't want to happen is for it to get an effect just from the laser, because I mean, that could be a photon rocket. So I have to be careful. So with the source on, and then I heat one end. Again, I don't want it moving. So all that's got to be checked out. Once I'm happy with that, I can then go. I put the source on, I can heat one end, I get it. Does the string move? It's a suck it and see experiment. I don't know. You guys are good experimentalists, like Michael Faraday. He would have done it for me. Unfortunately, he's not around. Perhaps one of you can do it for me. Thank you, Tim. That's it.